Hello.
Hello.
Hello. How are you guys? How are you guys feeling so far about the midterm tomorrow morning?
Definitely a
Uh,
little anxious.
A little anxious, yeah. Have you guys tried to practice midterm yet that he posted?
Yeah, I actually had like two questions on that
Uh-huh.
one.
Yeah.
Number five and number eight. Five, I just didn't know how you got the stereochem for the methyl on the
Uh-huh.
Diene file.
Yeah, number 5 and number 8. On Mascal's practice midterm, he posted
Oh,
here.
on yours.
Oh, I see this one. I see. Right. So for this one, number 5, this is a Diels-Alder reaction where wait, let me see. Grid apply. Okay. Right. So we're used to seeing the out and in groups on the carbons 1 and 4 of the diene. So let's say we know that this structure here is our diene and this structure here is our dienophile. So there's going to be a pocket between the diene and the dienophile like that, where I'm going to number this 1, 2, 3, 4, 5, 6, right? There are no groups on carbons 1 and 4. So there's no out or in groups here, right? We know the arrows for the Diels-Alder reaction looks like this, where we're going to move these bonds like that to give us this kind of product here, the cyclohexene base product of all Diels-Alder reactions, right? Where these atoms here are 1, 2, 3, 4, 5, and 6. So carbon 6 right here, we have the EWGs here, which let's say they are dashes, right? Because these two groups here are cis to each other. So I have to make them cis to each other. So if they're dash, like one of it is dash, the other one would also have to be dash as well, right? This one here did not react. That's part of the decoration of the dienophile. So that's just staying as that right there, right? You could think of this methyl group right here as trans to this carbonyl here. So we have to make that methyl group trans to this EWG right there. Since this EWG was a dash, this methyl group would have to be a wedge because they are trans to each other. And we could do plus enantiomer as well because it could be flipped. Right. Does that make sense?
Um, okay, so
Uh-huh.
wait, your key was a little different. So should I just follow this?
Oh, wait, hold on. Let me check the key. Wait.
Sorry.
Let's see. Uh-huh. No, it's okay. It's okay. Let's see. Number 5. Oh, right. So I got this from Nasiri's midterm when I took the class, and on the key, that's what I put. And I think the TA was nice. He gave me full credit because I wrote this as the answer, where I did not include stereochemistry at all, right? And I put a wedge on that methyl right there. But if you put dashes there, that's also correct. Right, but this is what I like put on the exam, which I got full credit for because I think my TA was like, I don't know, he gave me 4 points or something. But uh, this should be it right here.
Wait, so you also said it would be fine if the wedge methyl is a dash and then the two other bonds are a wedge because that's just the enantiomer, right?
Yeah, right. If this methyl was a dash
Yeah,
and the two bonds
that.
here
Yeah, that's
are
where wedge.
wedges, yeah, that's the enantiomer version of it, right? Uh-huh. Yes. But
Thank
if we
you.
had, no problem. If we had something like this though, like let's say we had like that,
Oh yeah, then that would
uh,
be a nice ceremony.
yeah, that would be Diels-Ader. This here does not change.
On that topic of like diastereomers and forming multiple products, I'm
Yeah.
gonna ask you a question. It was from one of Mariah's practices, and it formed 8 products. It was for Diels-Alder, but there was no pre-existing stereochemistry.
Yeah. So for that example,
Yeah.
that is when, let's say, your dienophile has two kinds of EWGs, like a nitrile or an NO2 here, right? So we know that if this is our diene right here, this EDG will push electrons down all the way to give that carbon there a partial negative charge. So we know that's the negative charge of this diene right here. But for the dienophile, right, we have two EWGs here. So the EWG could like withdraw electrons like that, giving this carbon a positive charge on that carbon, or this withdrawing group here can withdraw electrons from that dienophile, giving that positive charge right there. So we could have a partial positive charge on both carbons of the dienophile, where, let's see, the 8 different products.
I sent the picture to you.
Okay, let me see. Let me see that. Because I think this one here would give you
4.
4. Yeah,
Yeah.
there's another one.
That's how I got 4 on Mariah's as well, because there was no like pre-existing stereochem.
Yeah. And this one here that you sent me gives you 8.
Yeah. She just drew 2 of the products in the key and then just said forms 8 products.
I see. So that's when notice how for this one here there's 4 different ones because the dienophile, there's 2 equally positive charges on both sides of the dienophile. For the one that you sent me, which is, I'm trying to airdrop it, but I just read it here. This one here, this diene will have negative charges on both sides equally. In the example that I gave here, there was only one spot where the negative charge was. In this example, the negative charge is on 2 spots. Right? Which is why like we could flip it upside down 2 times. So let me show you what that means more clearly. The dienophile, let's say it's like this, right? Where the first thing I do for these Diels-Alder problems is I locate where my diene is and the dienophile is. I know this part here is my diene, and I know that part is my dienophile, right? And then once I have that, I'm going to rotate it in a way that I'm used to seeing it, which is like this, where the diene is going to meet up with that dienophile and create that pocket between them like that. Right? Where I know that this is an out group, that's an out group, and this is an in group because it's inside the pocket. Right? And we see that these are 2 EWGs right here, the ketone and the aldehyde, which will create positive charges equally on both sides of the dienophile. So now, the charges here, right? There's equal charges on like both sides of the diene and the dienophile. So we could react it like this, how it is right now, to give us something like this.
Okay, so there's 4 different ways that you could make the configurations of them, and then they each have an enantiomer, so that's how it gets to 8.
Yeah, right. That's right. That's right. Let me give you the 4 different ways that like how it's rotated. So that's one way. Let me how can I do this? Duplicate this. Erase all the markings here. Right. Okay. So that's these here will give you 2 products. The original one with the enantiomer. The other one could be this right here. The other 2, if we flipped the dienophile upside down like that, that's another set of 2. Right. The other set of 2 is, let's say we flip this diene upside down like that, where the pocket between the diene and dienophile is now here.
that's like the equivalent of like reflecting it on the y-axis, right? You're basically just like reflecting or on the top left one, you're just reflecting the diene on like the y-axis essentially.
Yeah, that's right. The flipping it upside down on the y-axis. This whole thing upside down, right? This one here, I flip this one upside down. The other one would be this thing, exact same thing, but the dienophile is also flipped upside down here, relative to the y-axis, like you said. Or like the x-axis, flip it upside down, like this, right? So this orientation here gives you two products, two products, two products, two products. So that's 8 products total. Let me make sure they're actually different. Right. Okay, that's different than that. That checks out. This is different than this. Wait, hold on. Okay, this looks like the same as this. Okay, but this is different than this. That's good. That's yeah. Okay, so if we have it that, we flip it. Two, four, two, four. Yeah, so imagine this reacting in that orientation, right? That's gonna give you two different products. The other set of products is gonna be if you flip the dienophile upside down. And then the third set of products is if you, let's see, flip this diene upside down. And then I'm trying to think of the fourth set because the fourth set is not gonna be the upside down again. Let's see. Two. That's the second one. Oh, actually, it is. Yeah, it's when you flip it again. So like you just gotta like try drawing it all different ways. Can I see the key for that? Like what she put for the key? You just gotta flip it upside down a lot of times.
Like it's in the key.
Yeah. Mhm. Okay. Yeah. So that's okay. I see. I see what she did. So yeah, so I was getting confused on my work here because this set here where you drew that pocket and that pocket is the same exact set as this set right here, because you will see that the ketone here is right next to that methyl group, and then this aldehyde here is next to this like isopropyl looking group right here, right? Which is the same exact thing as here. So this is actually the same thing as that. So there's only 2 sets here, right, that are unique, which is this set, like we are gonna keep the diene the same, which is the same configuration here. The dienophile here, we have 2 different EWGs. This one is different than this one because it's flipped upside down, right? The 4 other products is going to be like what you treat as your EWG, because we know that this is the pocket between the diene and the dienophile, like that, right? Where this is an out group, in group here, right? So we know in the endo role, the out groups are cis to the EWGs. The in groups are trans to the EWG. So let's say for this first set here, we treat the aldehyde as the EWG. That means all of the out groups will be cis to that aldehyde right there. But you could have also treated the ketone as the EWG. that means all of the outgroups will be cis to this ketone instead of the aldehyde. So that's the difference between the 4 other set of products. Like it's the same exact orientation, right? For this set here, it's the same exact orientation, but the stereochemistry is different, right? Because you're treating like a different EWG. So it's the same thing as this set over here. Like let's keep that same orientation, but you could treat this as your EWG for this set, or you could treat that as your EWG for that set. And that would change the stereochemistry because we want the outgroup cis to the EWG and we want the in-group trans to the EWG, right? So 2, 4, 6, 8 products from here, where these pairs here have the same orientation, same regiochemistry, but different stereochemistry. Same as these over here. These have the same regiochemistry, but different stereochemistry. Whereas these pairs here, they have different regiochemistry. And these ones here also have different regiochemistry, right? So it just depends on what you treat up as your EWG. Did that make sense?
Yeah.
Okay. Let's see. Shoot, there's a lot of questions in the chat. Do you only isolate when only reactants or other reactions too? So for anilines, which is this benzene ring with an NH2 right there, that will react with the fructose reagent instead of the benzene ring because this NH2 here is a stronger nucleophile than the benzene ring itself. So the acyl group from, let's say, fructose acylation would not be attached to the benzene ring. The benzene ring will not attack the acyl group. The nitrogen will attack the acyl group instead. There's another thing that would do the exact same thing, which is a phenol. A benzene ring with an alcohol on it. So this alcohol here is also a stronger nucleophile than the benzene ring. If you wanted to add a acyl group to the benzene ring, you would have to protect these groups here using a protecting group. But Mascal didn't go over that in lecture, and I remember someone saying like he skipped like 2 sections of this chapter, which I'm guessing are these 2 sections here which he skipped over. Did he go over that in lecture? I don't like protecting the aniline or protecting the phenol?
I don't think so.
Okay, yeah. So I
No, he just talked about like using it to protect certain positions so you can get the ortho position instead of the para position, but he didn't talk about like the actual group.
Yeah, he did the blocking groups with sulfonation, but I don't think he did acylating amines, alcohols.
Yeah. Acylating amines, that's how to protect that. But alcohols, it's a different way to protect. It is Williamson ether synthesis, where you create an ether from the alcohol.
Okay, yeah.
You do like NaH to deprocynate that alcohol, and then some kind of like alkyl group to create the ether, and then that creates the ether like that. And then from here, this is unreactive, and then you could do your fructose acylation like that. But I wouldn't worry about that.
Is there a way you can go back from the ether to the alcohol after you add it?
Yeah, so go from the ether back to the alcohol, you use let's say acid and water. Where the acid will protonate the oxygen to create that let's say OH plus, and then now that's a good leaving group where it's just gonna leave by itself, and then or the water could just attack it, right? It's just acid and water which will split up the ether into 2 alcohols.
And then for amide back to amine, it's just NaOH and heat.
Yeah, and amide back to, let's say this amine here with the acyl group, back to the amine. It is going to be NaOH and heat, or H2SO4 and heat. So it's acid or base here, where an amide to an amine, that's going to be the very beginning of 118C, that mechanism that you're going to learn. Right? That's how to deprotect that.
Okay, and then you only need to protect it for like Friedel-Crafts. So like, let's say if you were to do like destination, it would still go para.
Yeah. It's only for Friedel-Crafts reactions.
Okay, got it.
Let's see. Okay, so next question. Diels-Alder, does the EDG need to be cis to the EWG ortho?
Oh, like or ortho, or does it like not matter?
Um, so it depends on where the EDG is for the Diels-Alder.
Okay, so it's not
Right.
like it's not just like it has to be this. It just depends on where it is.
Yeah, right. In this case, it does have to be ortho because the negative charge is down there, positive charge is down there, then they have to be ortho to each other like that. Right. But your EDG could have been on the middle carbons like that. Right. Where it will donate electrons down like that and give a negative charge on the closest atom of the diene instead. If your EDG is one of the N carbons, like here or here, it will push the charges all the way down to the opposite end. But if your EDG is on the middle carbons of the diene, it will push the negative charge on the closest end of the diene like that. Right. So that's the difference. Where in this case, it does not match the charges because we know that this withdraws electrons. So what we have to do is we have to flip one of it upside down like that. Right. And in this case right here, these groups are not like next to each other. They're not ortho to each other. They're on different carbons.
What about the case like this, and then you have another EDG on the top position? Then would you have two possible flips? One where the charges are on both sides, so you just have you have four products, two isomers for each one then?
Yes, that is the case if you had another strong EDG, like another OCH3 or NH2, then you get four different products where you would also have a negative charge down here. But if that EDG was just an R group, like an isopropyl group, then I don't think this overpowers this EDG. This EDG will still put that negative charge on this carbon here because this R group here has no lone pair of electrons to donate. So I think the negative charge will still be on this carbon here. But if you had an EDG that did have lone pairs of electrons, then you would get that mixture of products, like the four different ones there that you were talking about.
Okay.
Right. Okay. When will hindrance in Diels-Alder give you NR? So the hindrance would be like this. If your diene is not fixed and you have two in groups like this, right? The in groups are meaning that the groups are inside of the pocket between the diene and the dienophile. That causes steric hindrance, which is very bad. No reaction. Right? But if it is fixed, then that actually speeds up the reaction rate because it is locked into the S-cis configuration where you are actually going to get a reaction like this here, right? And this is because this is locked and fixed into the S-cis configuration. This is not locked. This can actually rotate back to the S-trans, which causes a lot of steric hindrance. Doesn't allow for overlap between the HOMO of the diene and the LUMO of the dienophile. No
So
reaction.
it's only relative to the diene.
Yeah, only relative to the diene.
Got it.
Diene, yes. To diene.
Oh, for in general, for like the HOMO-LUMO stuff, do we just have to know that the HOMO of the diene reacts to the LUMO of the dienophile and how to like draw the resonance structures and just do that? Is that all
Yeah.
for that concept?
Yeah, and that's just a conceptual thing behind the scenes. You don't actually need to know it to predict the product, like how we did for like aligning the charges, the endoreal outgroup cis to the EWG, in-group trans to the EWG. That's just like behind the scenes thing. Like you just gotta know HOMO of the diene interacts with the LUMO of the dienophile. That's a conceptual thing. Right.
Oh, and then also is it HOMO-LUMO when you're doing electrocyclic reactions as well? Like the opening.
Yeah, it's also HOMO-LUMO of that as well. But where the orbitals overlap, like the reason why that happens is because the HOMO of the diene overlaps with the LUMO of the dienophile. Like this is the HOMO of the diene, LUMO of the dienophile. And the reason why the double bonds are able to like alternate around the ring like that is because of this overlap between the p orbitals here. There are no electrons here, no electrons here. The bottom lobe of that p orbital overlaps with that top lobe of that p orbital. The bottom lobe of this p orbital overlaps with that top lobe of the p orbital, which allows the flow of electrons around that HOMO-LUMO interaction.
I see.
Okay. When will hindrance in Diels question F on Maria's practice? How does it yield 8 products?
Oh,
Okay.
that was the one that we already talked about.
Nice, nice. So that's talking about like the regioselectivity, where if we have equal charges at the dienophile, it could flip upside down. The stereoselectivity part of it is like, since we have 2 EWGs, you could choose one to be EWG, which would be cis to the outgroup. And in the other set of products is if the other EWG is the one that is cis to the outgroup. So that's going to give you different products from there. But for predicted product, like 8 products like that on the test, I've never
Yeah,
seen
I doubt that would happen. I just saw one example in Mariah's, and then Evans, she put one example like that. But like the rest have been like,
yeah, I see.
I was looking at the Nasiri midterms on, I think I forgot where it was, the past Nasiri midterms. She's asking for like the ozonolysis mechanism, and like she asked some pretty crazy questions on her midterms actually.
Oh, shoot. On Levens, like ozonolysis ones? So like was it in a ring like that? Or something like
I think so. I think so.
Oh yeah. Yeah, that ozonolysis. Oh my gosh. Right. Just cut double bonds in half and put oxygens in the middle. Like that. Right. Okay. Nomenclature. If we have multiple common name substituents on the benzene, how do we determine which one takes precedence? So that is like,
isn't there like a
mostly,
list of priority?
yeah, there's a list like
Carboxylates are the
memorization.
highest, aldehydes and ketones are like after that.
Yeah. Another way to remember that is like the more oxidized the group is, like the more double bonds it has to electronegative atoms, or the more bonds it has, like the carboxylic acid derivatives, like the carbonyl, and then the oxygen there, the more priority it takes. So that's just a memorization thing from the nomenclature list. For example, if we have 2 substituents like this, OH, and the methyl group right there, if it was just this benzene with the methyl group, that's toluene.
yeah.
If it was just the benzene with the alcohol, that's phenol. We choose the group that is more oxidized, or the one that has like more bonds to electronegative atoms, which is the phenol, because there's oxygen there.
For sure.
So the phenol would take priority over the toluene there.
Okay.
Oh, also I've seen like a benzene as a substituent be called a phenol group and a benzyl group. Are those both names? Like I swear, like I've seen both of those used.
So they are different because let's say we have something like this. I don't know. Let's just say this is the main chain right here. Right? And then a substituent of a benzyl group is something like this. Wait, actually, it's gonna be easier if I draw it like this. Like this right here is the main chain, and then this is the fragment right here. This is the benzyl group, where you have a CH2 first, and then the benzene ring. But if you have this substituent where you have the benzene ring right away with no CH2 separating the main chain and the benzene ring, this is the phenyl group. Right? The benzyl group, the benzylic carbon is there. The phenyl group, there's no benzylic carbon separating the main chain, whatever the main chain is, and the substituent. Right? This is the substituent. That is the substituent there. And
And
then
then how do you tell when the benzene is like substituted? Is it just if the chain is longer than 6?
yeah, if the chain here is longer, or if you have a very important functional group, like let's say we have something like this right here, like alcohol. Then we have that, and then we have cyclopropane, and we have alcohol right here. Alcohol has the highest priority group out of all of that structure. So this is our number 1 carbon here. This is gonna be number 2 carbon because this is our next substituent. This is number 3 carbon. So this is 2, benzyl because we have a benzylic position here. Cyclopropanol. And the 1 is optional here because this is in a ring. If the
Yeah.
alcohol was not in a ring, then the 1 is required.
Okay, so it'd be propan dash 1 dash all.
Yeah, propan dash 1 that's the optional one. Propan dash 1 dash because it's in a ring.
Yeah.
Right. Okay. General tips and tricks for NMR. Okay. Okay, so here's my thought process. DOU always first. IR, figure out your functional groups. Third step, HNMR, get your specific fragments, not the full piece yet. Fourth one, attempt to piece the fragments together. It's all trial and error. Like you gotta try a lot of things. It might not work. You just go back
Or
and start again.
I guess I was talking more about like any type of benzene specific related NMR
Oh, okay.
or diagnostics.
Uh-huh. Right. So that's good. Verify with the formula, DOU, IR, HNMR. Okay, so for benzene, are you familiar with the ortho meta para like patterns, like how ortho between 6 to 8 you're gonna have a doublet, a triplet, doublet, and then for meta,
You mean so the hydrogens are ortho to each other?
yeah, if the hydrogens are, or I mean, if the R groups are, oh, are you talking about J values? That's a separate concept. Like if we have two R groups like this that are ortho to each other, we have 4 benzene hydrogens here. Like these are the 4 benzene hydrogens. Let's say this is A, B, C, D. They are different from each other. This is gonna be A, B, C, D. Because this hydrogen A here only has 1 neighbor, which is why it's a doublet. This hydrogen B here has 2 neighbors, which is why it's a triplet. Hydrogen C also has 2 neighbors, triplet. Hydrogen D has a 1 neighbor, doublet, right? But for meta, if your 2 R groups are meta to each other, right, we are going to have something else. We're going to have, let's say, this is A, B, C, D. Hydrogen A has no neighbors, 0 neighbors. So it should show up as a singlet. B has 1 neighbor, doublet. C has 2 neighbors, triplet. D has 1 neighbor, doublet.
Would it be like I feel like a lot of the times though the peaks are super like it's hard to read them individually like this. It's like really
Yeah, it is hard to read them. Like I saw in the practice exam, like it's really hard to read them. And then I saw he gave you J values instead, right? So that's a whole different thing.
Yeah. So the J values, I'm assuming, are used because like we had a tri-substituted benzene, so I'm assuming that's when like the J values are more helpful. But like,
Yeah.
if di-substituted, like the actual peaks are more helpful. But even like on Helix's midterm, I was like confused why something was ortho because I was like ortho is going to be the 4 1H's. Or no, it was meta. It was meta, and I thought it was ortho, but it was because like the 1H singlet was still like split, but it was very close together. So I guess it's just considered a singlet.
Oh, right, yeah. It's like very hard to see like with the peaks, I guess.
Yeah.
But for Helix exam, was it di-substituted or tri-substituted
It was
for the
it was one of the ones that you put, I think it was midterm. It was midterm 3B. Or was the midterm B? Yeah, midterm 3 section B. Like you see how there's 4 peaks in the benzene, and then like the more zoomed in perspective, the one furthest to the right. I didn't think of that as a singlet, but I guess he did consider that a singlet.
Yeah, I think they just have a complex splitting because of the J values, which is why it's like the doublet of like the triplet or something like that, like the many subpeaks like there. That's the J value talking there.
Okay. But like if it's super close, you can just assume singlet.
Yeah, just like this right here.
Like so, and yeah, so in this case, you just ignore like the splitting and you look at just the total overall peak and consider that.
Yeah,
Yeah.
it's substituted.
Right. Another big sign is that there's 4 benzene hydrogens, so that means that we have 2 substituents. So it's either ortho, meta, or para if we have 4 benzene hydrogens like that, which is di-substituted. Which in this case, we have that singlet peak right there, which is this meta, not this this group, this hydrogen here in between the 2 groups right there with no neighbors, which is that
Oh,
singlet peak.
and you know that because the other one has a triplet, it has to be neighboring 2, so it has to be ortho or it has to be meta in this case.
Right, it has to be the meta to the groups, right? Meta to the 2 groups. The hydrogen with the triplet is meta to the 2 groups, right? Right. Where the J values for benzene rings are this right here. If the hydrogens are ortho to each other, they're gonna have around 7 J value. Meta around 2, para around 0 or 1, right? Most likely like 1. So if they have matching J values, they have a relationship with each other. And if the number that they match is around 7, they are ortho to each other. If the number that they match is 2, they are meta to each other. And 0, para to each other.
Oh, and what was the thing about the para? Reminded me in lecture, he said para is 0 to 1, and then he said negligible next to it. Is that because you typically don't see J values for
Para. Right. And another way you could think about it is that let's say para hydrogens, they are like right across from each other. And think of symmetry here. This will go into the vocab question. There's symmetry here, which makes it negligible, which this overlaps with the symmetrical internal alkyne like this. If you have a symmetrical internal alkyne like that C triple bond C peak, which we are used to seeing as a sharp peak at around 2100 to 2300 in the IR, would be negligible because of symmetry. This is a symmetrical internal alkyne.
Oh,
So,
I remember one of the questions was that there is one diagnostic peak for an alkyne. And is that because the 2100 to 2300 could be the nitrile group as well? So it's not considered diagnostic? Is that the reason why?
oh, right. So the reason why it's not diagnostic is because of the symmetry here. Since there's symmetry, because they gave us 3-hexyne, this is 3-hexyne right here, it would be considered negligible. Like that the peak would not be sharp anymore. It could be like very small and tiny, which is not sharp and intense. It's small and almost negligible. But if you had an asymmetrical internal alkyne like this, then you would see a sharp peak at around 2100 to 2300. And that would be considered a diagnostic peak. Diagnostic meaning that we get to diagnose what kind of functional group is on the molecule, which is in this case is a triple bond. The reason why the 3000 sp3 CH sharp peak is not diagnostic is because it doesn't allow us to diagnose what functional group is on the molecule. That is almost always there for every molecule. It's like plain and boring. Like it doesn't tell us what functional group there is. It's not diagnostic. But this peak here is diagnostic because it tells us exactly that we have a triple bond, either alkyne or a nitrile, like you said earlier. Does that make sense?
Yeah.
Right. This is not diagnostic because it doesn't tell us what functional group we have. That's just an alkane. Right. Okay. Let's see. Okay. Can you do a quick example of an alkyne with HBr? Yes, alkyne. I'll show you different types. Terminal alkyne and 2 types of internal alkynes, symmetrical and asymmetrical. Okay, so for terminal alkyne, let's say we have something like this, and we react it with HBr excess, right? Think of this back in the midterm 1 material with alkenes. This is going to be Markovnikov, where we want to form the more stable carbocation, which is the more substituted position here. That means that the less substituted position is going to grab the H, kick out the Br, and form this carbocation right here, right? This triple bond now becomes a double bond because it used one of its bonds to create that bond with hydrogen right there on the left subside. Now, the Br minus that got kicked out is going to come back, attack that positive charge to give us this Markovnikov position here. On the test, if you see one equivalence on the arrow, you stop here if you see one equivalence. But we have excess, so we're going to bring in a second equivalence of HBr, which this carbon here is going to attack the hydrogen to form the more stable carbocation, which is this position here. And then Br minus is going to come back and attack that carbon right there to give us this geminal dihalide, where the bromines are on the same carbon. Geminal dihalide. They have a 1-1 relationship with each other because they are on the same carbon there, right? If it was Br2, like X2, then it would be a vicinal dihalide. They would have a 1-2 relationship with each other. But we have HBr, which is different than X2, which is different than Br2. Okay. So now let me go over a different thing with you because that was the Markovnikov version. There is an anti-Mark version. If you have HBr and ROR with light, think of anti-Mark, where the bromine is going to attach on the left subside, which is this carbon here. So let's just draw that in. We're going to get two different types, the trans version and the cis version, where the trans version is major and the cis version is minor because of steric hindrance there, right? So that's for predicting the product if you have ROR, HBr with a terminal alkyne. Okay. For symmetrical internal alkyne, like let's say we have this symmetrical internal alkyne here, and we have HBr excess, it doesn't matter which carbon we add the Br. They're both equally substituted, and they're both symmetrical. So I like to number it 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Where we could attach the bromines on carbons 3 or 4. Right? Carbon 2 had a methyl. Carbon 5 had a methyl. Let's put it on 3. 1-1 relationship, geminal dihalide, because this is HX, not X2. If we put the bromines on carbons 4 instead, that's the exact same thing. It's just flipped and rotated because of the symmetry here. But for asymmetrical one, we're going to get two different types of products. Like let's say we have this asymmetrical internal alkyne like that, and we do HBr excess, we get these two different products here. That and the other carbon of the alkyne, because those are different now. They are constitutional isomers. This set of bromines here are closer to the ring, but this set of bromines here are further away than the ring because of asymmetry. Right. Any questions on the alkyne reactions with HBr? Okay. Ready to,
I had a question when you have like the halogens on like the terminal part of the alkane and then like the second to terminal part, if that makes sense, and you make the terminal alkyne from that using like a double elimination mechanism with the NH2 and NH2. You need 3 equivalents because it deprotonates the terminal alkyne and makes the alkenyl, and then you have to reprotonate that.
yes.
But my question is, why can't you just use 2 equivalents? Why is that a thing?
Right. So that's the confusing concept, because after 2 equivalents of the strong base, you already get to your terminal alkyne like that, right? Where you could just stop here.
Yeah.
But because we have, this is just a conceptual thing. This sp hydrogen here is acidic. So some of it will actually be deprotonated to give us the alkyne anion here, right?
So it is deprotonated by itself?
It just deprotonates itself because whenever you use 2EQ right here, it's kind of weird because the 2EQ will get rid of one leaving group and the other leaving group. But there are still like leftover because in lab it's not that clean. In paper it looks clean like that with just 2EQ.
Oh, so like practically speaking, it doesn't work like that.
Yeah,
Okay.
it's just a lab speaking way. Like we want to go all the way down to the deprotonated version to make sure there's no leftover reactant molecule here. We
Like
will
it's a
get
high yield reaction basically.
right. It's a
Okay.
practical lab thing. Right. Okay. Number one, A and B in Mascal's vocab. Okay. So I went over the 1A already with the 3-hexyne. 1, 2, 3, perfect, like that, where there is a triple bond there, which we expect to have a sharp peak at around 2100 to 2300, but because of symmetry, it makes it small and not intense and sharp. So it's almost negligible if it's symmetrical, right? Negligible. And there is symmetry because that is an ethyl, that's an ethyl. I didn't know about that until he released the key. Like I also put 1 because I always thought that this triple bond there would always have a sharp peak at 2100 right there. Like I was never tested that concept. Like the symmetry reduces the intensity of the peak. I always saw that sharp peak there at 2100 on all the triple bonds. But I didn't know that symmetry like reduces the intensity of the peak. I got this one like wrong when I tried it. So that is no diagnostic speak right there. Right. B, the preparation of windbutane from, oh yeah, so this is the one where we went over with Darshan, where 1,2-bromobutane looks like this, and we want to create 1-butane like that, the terminal alkyne. Whenever we want to make a terminal alkyne from this vicinal dihalide, we always have to use at least 3 EQ of strong base. 2 EQ would give you this, and then it looks like you stop here, but in like lab, this is acidic. You get some of this and some of this left over, the original starting material. But in lab, we want to get rid of that and completely turn it into this. So that's why we gotta overdo it with at least 3 EQ to make sure and ensure that it goes all the way down to this product to get a higher yield. Right, so that's why we need 3 EQ, at least 3 of base. But if it was internal alkyne like this, then you only need 2 EQ. Because once you get this, there are no acidic hydrogens on the internal alkyne here. There are no hydrogens on this carbon, no hydrogens on that carbon there. Okay. Any questions on that? Or did that help?
Yes, thank you.
Yeah, no problem. Okay, he never showed us the part. Yeah, right. Look, NH2 to NO2, CF3. Yeah, so that's talking about the oxidizing reaction where we said that the NO2 can convert into the NH2 using a reducing agent such as H2PDC or Clemmensen reduction, zinc, mercury, HCl. This is the reduction step. We're reducing this nitro group to the aniline. To oxidize this aniline back to the nitro group, we use an oxidizing agent like MCPBA or some kind of peroxy acid.
So you can't use Jones for this? You can't use Jones?
Yeah, you can't use Jones for this. Jones will oxidize something else. It would oxidize an benzylic carbon with 2 hydrogens. Right, let's go back here. Jones into the carbonyl. right? So this is important for synthesis because
I don't remember Mascal ever talking about MCPBA. I remember he said H2 like pretty much reduces everything with the palladium catalyst, and then he just talked about Jones. I don't remember him ever talking about the MCPBA.
Oh, right. He only went over like going from the alkyl group back to the carbonyl. But he skipped over this part here in lecture as well, like going from the amine to the NO2, like how he skipped like the protecting the amine with the acyl group or protecting the phenol with the Williamson ether method, synthesis method.
Okay.
Right. Okay. Can you go over the NMR problem on Mascal's midterm 2? Yes. That takes a long time to like deduct everything, but let me go over that at the very end where let me answer the other quick questions first. When using NBS, do you go for the radical? Okay. I think Amar got that one. Okay, Amar got that one. Okay. Let's go over the NMR problem. Okay. So this NMR problem here, I don't agree with the J values, and I'll tell you guys why. First, I calculate the DOU of this chemical formula, which is going to be 2 times 9 plus 2 minus 7 plus 1 all over 2. That's 18 plus 2, 20. 20 minus 7 is 13 plus 1, 14, 7 DOU. So if I have at least 4, I'm going to automatically guess I have a benzene ring somewhere in the structure because of the 3 double bonds and the ring. And we could double check that by looking at the H and MR. If you see peaks around 6 to 8, then those are your benzene hydrogens, which we do have peaks here. So this fragment checks out. I do have a benzene ring somewhere. Okay, the next thing I do is look at the IR. Right? Ignore the fingerprint region. This 1600 peak here is the alkene. C double bond C peak, which are going to be the C double bond Cs of the benzene here. This sharp peak here, around 2100 to 2300, is the triple bond region. So we either have an alkyne, C triple bond C, or a nitrile, C triple bond N. I'm going to look at the molecular formula here. I do have an N in the molecular formula, so I'm leaning towards N. There's a possibility that it could be an alkyne, but I'm leaning towards the nitrile because of the nitrogen in the molecular formula. So in these spectroscopy problems, it's a lot of piecing the fragments together from different sources, like the formula, molecular formula, HNMR, IR, J values, stuff like that. A DOU as well, right? And then the 3000 region, that's the normal peak where you could say that that's the 3100 sp2ch, which are going to be the hydrogens of the sp2 carbons here, right? So those are the important information for the IR. Now let's look at the J values. I'm going to summarize that again here, where if the hydrogens are ortho, they will have around 7. If they are meta, around 2. Para, around 0. Okay. So since I'm guessing we have a nitrile, I'm just going to put that nitrile somewhere random on the benzene ring. Let's put that nitrile here, right? Now, we already considered 1, 2, 3, 4, and a triple bond represents 2 DOU. So that's 4 plus 2, that's 6 DOU. 6 out of 7 DOU, we are missing 1 DOU, which that 1 DOU could be a ring, or it could be a double bond, right? So we see that there are 3 benzene hydrogens between 6 to 8, which means that we have 3 substituents on the benzene ring. Let's label those hydrogens A, B, and C. Let's say that this is A, B, and C. And I'm going to draw out the J values like this. 2, and then B has 2 and 7, and then C has 7, like that. Okay. Right. We see A and B have matching J values of 2, which means that they are meta to each other. So I'm going to say HA is right here and HB is right here because they are meta to each other from the matching J value of 2. B and C, they have matching J value of 7, which means that they are ortho to each other, right? So the answer key says that HC is right here, where there are 3 hydrogens in a row like this. I don't agree with that. I think it would just be right here, HC, because yes, the hydrogen C and B are still ortho to each other, but we also see A and C are ortho to each other. So I would expect another J value around 7 with A and C as well to show that they are also ortho to each other. But we don't have any J values for A and C that show that they are ortho to each other.
But also, can't you tell that none of them are triplets? So it's not possible for hydrogen to have 2 neighbors.
2 neighbors. None of them are triplets.
Yeah, they look like doublets, right?
Doublets.
So
Oh
then you
yeah, right.
have one neighbor.
Yeah, that's another way to show that that's good reasoning. This here is going to be a triplet because of 2 neighbors here, but there are no triplets on there, which is another reason to not agree with this HNMR for the key, right? So there are 2 reasons why I don't agree with this now: the J values, and also like there's no triplet here on the HNMR, right? But this is what is shown on the key, which is weird. Okay, so now we already considered those peaks, and let's now count how many carbons we used up. 1, 2, 3, 4, 5, 6, 7 carbons. We have 9 carbons. We have 2 more carbons left to use. Okay, let's look at this peak here. This peak is going to represent 2 hydrogens. That's a triplet. And what do you notice about that peak right here? Like, what is it nearby based on its ppm value? Like, what does it mean if a hydrogen peak is around 3 to 4? What is it next to? Right. So since it's between 3 to 4, it's going to be next to an electronegative atom, where our only electronegative atom left is this oxygen right here. So let's put that oxygen right there. And whenever you see an oxygen, you automatically think that there's going to be some kind of carbonyl or alcohol. But we know there's no carbonyl here because at the 1700 peak, there's no sharp peak at 1700. There's no alcohol because there's no broad peak there. So this this oxygen here is most likely part of an ether, where ether would not show up as any peak at all in the IR, right? So let's draw those 2 hydrogens as these 2 hydrogens right here. And we know those 2 hydrogens has 2 neighbors, which are going to be these 2 neighbors right here, right? And then to make the 2 neighbors, we can't add another carbon here because that already exceeds the number of carbons we could use. We used 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't add another carbon there. That's a 10th carbon. That's way too many. So we got to connect it like that, which makes a ring. And this ring here counts as 1 DOU, which fulfills all of the 7 DOU now. So that's 1, 2, 3, 4, 5, 6, 7 DOU from the triple bond there. So that counts out for that. So now let's make sure, verify with everything. The formula, 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, good. 7 hydrogens, 1, 2, 3, 4, 5, 6, 7, good. 1 nitrogen, good. 1 oxygen, good. And then all of the HNMR peaks doesn't. I don't agree. I don't agree with this part here because this hydrogen C, like Darshan said, should be a triplet because of 2 neighbors here, but we don't see any triplet here. And this hydrogen C and A are ortho to each other. So A and C should have J values that are around 7, like let's say 6, but it's not there. So I don't agree with this HNMR graph and this molecule here. Right. Did that help, Joanna?
Yes, thank you.
Yeah, no problem.
Oh, I have one last question
Yeah.
before you to go. I was confused because I remember peroxide like radical addition with HBr was from chapter 12, but I'm seeing it again. Can you just go over like the NBS like radical addition and the like because is there still peroxide radical addition? I'm kind of confused on that.
Right, the peroxide meaning like the H2O2 or ROR that could roar.
Yeah,
thing.
that stuff.
Yeah, that is for alkynes. You can still see that coming up for alkynes like we did earlier. Specifically terminal alkynes. Like when you see HBr and ROR peroxide with light. Whenever you see peroxide, always think of anti-mark. Where you always add the bromine.
Or I just think of like okay, so or mechanistically, I know that the RO becomes ROH and it makes a bromine radical, and the bromine radical creates the more stable radical. But my question is, where does the new radical come from? Does that come from like yeah, right after that intermediate you drew? How does that radical get quenched? Like where does that
that's good. That will get quenched by HBr.
Another HBr. So it's like a propagation step. So it creates the Br radical so it can do it again.
Yes, that's correct.
And then okay. And then in the case of the NBS, does it quench the radical from the Br2 and then do the same thing with the propagation?
Yeah. Where when you see NBS, assume HBr is around in the solution, where the hydrogen from the HBr is going to be there in the mechanism. But Mascal didn't go over the mechanism of that, and there's a high likely chance that it's not going to be on the mechanism question because he didn't go over the mechanism of that. But it's going to come from HBr, the proton source, to quench the radical that gets formed.
Okay. And for the NBS, is that just for alkenes or for conjugated dienes, or like what is that for?
NBS is
because that takes away the allylic hydrogen, right, and creates the radical in the allylic position.
Right, and then in this case we have two allylic positions. We are only going to worry about the allylic position that is the more stable one, the more substituted one, which is that one. And then we could see its resonance like this, which we are going to get two different kinds of products. That right there and right there. So if there's multiple allylic positions, choose the most stable one and then draw its resonance structure.
Okay, and then and then in this case, this gets quenched by HBr.
Oh, right. So in this case, I just realized that it doesn't get quenched by HBr. It's gonna get quenched by Br2 because what is going to be attached to the radical is not H. It's gonna be a Br.
A Br, yeah, and then
right.
The thing. Okay.
And then it's
I was just confused about that question on the midterm with the deuterium bromine.
Oh, right.
That one, like, it was kind of odd. Do you think you can do that one real quick?
Yeah. So that one right here. Let's say we have this allylic position, DBr and ROR with light. We are gonna get this product here with the D. So that's what he wants. But let's say this is only possible if you are in low concentration.
Because I was thinking that the H attaches first and it forms the radical on the secondary position, right? And then the Br attach after that.
So right. Well, let's see DBr and then the let's see, and then that's gonna create. Let me try and think about this.
Because I feel like usually the ROH is formed and the Br radical just but it's different.
Right. Wait, let me do the whole mechanism. Like the one that you're thinking about. Let's do the initiation. Like how the ORs get formed already?
Yeah. I know that.
Yeah, right. So that's gonna be like that radical there. This is the original one with like the one we're used to. Once we get that, now we bring in the
I remember it being the OR radical reacts with DBr, or let's just say it was HBr to form ROH plus Br radical. That's what I remember.
Right. The OR radical here would react with the DBr first to create DOR and then create that Br radical.
Yeah, exactly.
And then that's the propagator right there. That would propagate the chain, right? Where we want to form the more stable radical, which is gonna be this. Okay, there we go. Now this is anti-mark because you notice how the bromine is on the anti-mark position, like the less position. And then from here, since we don't have HBr, we have DBr. We're gonna have a D on that carbon, which will give us this product here. So this is your product. If you have this in high concentration.
Yeah, because that was different from what the entropy was, which is why I was confused.
Yeah, this allylic one here only works if this is in low concentration, which is why we barely use this in low concentration. We use the NBS route, which we don't have to worry about concentration at all because this NBS automatically keeps it at low concentration.
Okay, and
But
the NBS is what creates the allylic position for the D to attach.
wait. That's for the NBS route. That's like when we went over this right here with the radicals at the allylic position, right? Where he already gave you the product, so you don't have to worry about concentration in this case. You don't have to worry about, like, normally it goes through here, but he gave you this part, which is gonna go to a whole different kind of mechanism. Right.
Okay, I got it.
Right. Which that mechanism is like this, like once you have the Br radical, that's going to form that allylic radical, which is stabilized because it could do resonance with the double bond nearby there. And then from here, we bring in the DBr to propagate the chain further by grabbing that D and kicking out the Br radical, like that.
Okay, that makes sense. Yeah, that's just like completely different from the mechanism I've seen before, so I was kind of confused.
Right. It is different because normally, like, you wouldn't get this. You would get this, like what you expect, but he gave you that because he's gonna make you assume that it's in low concentration.
Okay, thank you.
Yeah, no problem. Okay. Any other questions, guys?
Oh, just a quick question.
Yeah.
For mercury,
Uh-huh.
is it anti-Markovnikov or Markovnikov?
Markovnikov. When you see mercury, H3SO4, always think of Markovnikov. H2SO4, water. And so let's say we have a terminal alkyne like that. That's going to add a carbonyl at the Markovnikov position, which is the more stable position, more substituted position there.
Okay, it goes to like it always gets tautomerized.
Right. It goes through this
Okay.
intermediate first where we are adding an alcohol on the more sub position, but since this is an alkyne, we make the alkyne into a double bond alkene. But this is an enol here, which always tautomerize into the carbonyl. Nice. And if you had an internal alkyne, right? If you have a symmetrical internal alkyne, you only get one product. If you have an asymmetrical internal alkyne, you get two different products.
Okay.
Right. Okay.
But is that an aldehyde or
for
no, okay, never mind.
yeah, that's hydroboration-oxidation on terminal alkyne. If you have a terminal alkyne and react this with hydroboration-oxidation, hydroboration, then you would react with the less subside, which you would get the aldehyde here after tautomerization.
Okay.
That's the answer.
And like, what do you think will be like the most probable mechanism he might test us on?
The most probable mechanism, let's see, he tested on the radical stuff
Yeah.
with the DBr. So that's kind of unpredictable because I predicted it to be a benzene kind of reaction mechanism, like nitration, sulfonation, halogenation over the phenocast ones. So I would say those, but the niche ones, like the really weird ones, like the radical stuff, it could be, let's say, like, how did we get to the kinetic product or thermodynamic product, depending on the temperature? So he might give you a conjugated diene, and then he might give you X2 or HX, and then he draws like a kinetic product or thermodynamic product. And then with D, like deuterium D something in there. And then instead of making the H invisible, you have to draw that D out for the kinetic or thermal product.
Okay, that makes it. Yeah.
Yeah.
Thank you.
No problem. How are you feeling so far?
I think I'm okay with predicted product and synthesis. I'm really gonna mess up on like the NMR and the vocab.
Yeah, that would be me too. Like if I'm taking the class and I'm in your shoes, like the synthesis, predicted product and mechanism, I would be okay at. But the vocab, like I messed up like on the key. Like this first part here, I got it wrong. Like the A, I said one. And then the NMR, I don't like blame you guys because I don't agree with the NMR HNMR here.
Oh, I think you got the wrong. Like the key said CN was meta.
Oh, meta to it.
Yeah.
Oh, I see. Oh, okay. Dang. There you go. What did you tell me, Sujan?
No, I just checked right now, so I was like, huh.
Oh, I see. Okay. So this is supposed to be meta to it. that would make more sense then, because that would be no longer
Yeah.
yeah, that with that singlet is that singlet right there. And then
Oh, okay.
these other ones here are like doublets. All right.
Oh yeah, I
Over there.
mean they still have like a oh yeah, that one.
Yeah, the other group over there. Yeah, where these are doublets right here. Okay, now these make sense, but the J values still don't make sense.
Oh wait.
Oh, wait. Oh, this is the key right here. The J values do would make sense
Yeah.
then.
Yeah.
It would make sense. Wait, did he change up the key? Let me check.
I don't know.
Hold on. Let me see the HNMI. Oh, it is meta.
I didn't even know he posted a key, like I don't know when.
I see. Oh, you're right. It is meta. So now, yeah. Now this does check out. It does check out now.
Okay.
Yeah. It doesn't need to be there anymore.
Okay.
Okay. It makes more sense now. Makes much more sense now.
Uh-huh. When it's like between the 4 to 5 range, does it mean it's just close to the O oxygen?
Electronegative atom, close to the O. Yeah.
And
What-
what about 3 to 4?
3 to 4, like think of that, like actually think of it as 3 to 5, actually,
Oh.
or 3 to 4 is the electronegative. And if it's between 2 to 3, that's the alpha region, where
Okay.
the hydrogen is alpha to a double bond, or alpha to a let's say triple bond, or a terminal alkyne itself, like next to a double bond, a lot of double bonds, or alpha to a carbonyl, which is another double bond, right? Which we see that this peak here is alpha to like is alpha to that double bond right there.
Yeah.
Uh-huh.
And like last question. How do you know like the oxygen is in that place but not in the other carbon?
Right. Let's try that. That's why there's a lot of trial and error. If we put the oxygen here, right, these two hydrogens will have no neighbors, singlet. Singlet as well. But that's not singlet, that's not singlet.
I meant like closer to CN, because like if you put it in a different
Oh.
they have different distance to the CN.
Oh, right. So that's why those are the two different products that he gave.
Oh, okay.
Uh-huh.
Okay.
Yeah, it could be that as well. It's a
Oh,
good
I
question.
thought there was a way to like distinguish.
Oh, no way to
Okay.
distinguish. Yeah.
Yeah, that makes sense.
Dang, I gotta put a note on the video. like when I said there was like a typo here, like this would actually make sense now, based on the thing, like with the meta. Dang. Ooh, good.
Okay, yeah,
Dang.
thank you.
Yeah.
I do well.
Yeah, I think you will do well, because you've been like coming here like very early, like right after the midterms, and like weeks early and stuff like that.
But I don't know, because predict the product is just a little part of it. It's mostly, it's like, yeah, NMR and vocab is like a big part, so I just feel like I have luck. Yeah.
It is a big part. Yeah, it's very bulky. I know. How are you gonna study for that? Are you just gonna like wing it and like hope for the best for those parts, the vocab and NMR, or are you gonna like do some studying for that?
I think for the last hours, I'm just gonna try to do more NMR problems. I'm just gonna give up on the vocab.
Oh yeah. I see. Yeah, that's what I would do too.
Yeah. Well, yeah, thank you so much, Ray.
Yeah, no problem, Sinyan.
Yeah, have a good night.
You too.